Remember from the last lecture, sorry for the interruption. Unwanted interruption was there. All right, so we take start from Laplace transforms of derivatives. I mean, this is the ultimate objective that we have to talk about. When we look into the physical phenomena, the mathematical formulation will turn out to be differential equations. And from the differential equations, we have to deal with derivatives of certain order. Depends upon the differential equation or system of differential equations. So we need to talk about Laplace transforms of those derivatives involved in the given differential equations. So for example, as we have seen in the last lecture, if there is a first derivative, so how do we look into the Laplace transformation? So the Laplace transform of f prime of t will turn out to be s times f bar of s minus f of naught. So everything should be there in order to look into the Laplace transformation of first derivative. Well, behind the scene, we all know about the conditions that f of t should be continuous for all sort of values. For all sort of values of t greater than or equal to 0, should be of exponential order, and on top of that, f prime of t should be piecewise continuous on the same interval, t greater than or equal to 0. when we look into this Laplace transform of second derivative, so there you go with the expression s square f bar of s minus s f of naught minus f prime of t. So you see that there should be f of t, f prime of t, so that we can look into the Laplace transformation for the second derivative. The process of finding the Laplace transform is known as transformation, where f bar of s is basically Laplace of f of t. F of 0 is the value of f of t at t equal to 0. And if, in general, there is nth order derivative, how do we find the Laplace transform of nth derivative? So this is all with the formulation. Everything will turn out to be function of s. So this is all. The Laplace transformation is from f of t to f of s. So we need to provide all sort of things to the right hand side so that we can have Laplace transform of the nth derivative. If we are interested to see the proof, so take into consideration the first one. By definition, we know, the Laplace transform of f prime of t will turn out to be integral over the interval from 0 to infinity. Now, whatever there inside the curly parenthesis, it will be multiple of e raised to power minus st with variable of integration being t over here. Is it all right with the visibility and the voice, please? Any one of the CR could reply to me, please.
Yes, sir.
Is it all right?
Yes, sir, it is all right.
All right, thanks. All right, so by definition of Laplace transform, to anything inside the curly parenthesis, so if it is f prime of t, so by definition, it should be multiple of e raised to power minus st over the interval from 0 to infinity, with the variable of integration being t over here. And then further, we know the formula. How do we look into the integral? So keep e raised to power minus st as it is. Now the integral to f prime. So by utilizing the fundamental theorem of calculus, integral and differential, they will cancel out. And we left with the original function, f of t, over the interval from 0 to infinity. And then integral to f prime means f of t. Derivative to e raised to power minus st will turn out to be e raised to power minus st times minus s. So minus s is adjusted outside the integral. So minus into minus plus. So if you look into the first component to the right hand side, because of this definition, f of t is of exponential order. So it will converge, this whole combination will converge to 0 for a very large value of t. As t approaches to infinity, this whole combination will turn out to be 0. With the lower limit, we will left with minus f of naught. And if you look into the integral, it's a perfect definition of Laplace of f of t. So s times Laplace of f of t. So rearranging terms with the right hand side. So we eventually have Laplace of f prime of t equal to s times f bar of s minus f of naught. F of naught is basically the value of f at t equal to 0. And f bar of s is Laplace to f of t. So this is all. We will compute Laplace to first derivative of f. Pretty much on the same line, you can look into the proof, the extended version. for f double prime, and for the nth derivative. You could also look into the proof for the nth derivative by utilizing the mathematical induction, because there are infinitely many values, of course. For n, we are not sure about n. What is n? We assume that it is going to be pretty high derivative. So normally, the problems that we are going to talk about, they will involve either the first or at maximum second derivative. So if it is first derivative, so the Laplace of f prime will turn out to be that one. And if it is second derivative, so it will turn out to be that one. So all we need to know the value of the function at t equal to 0, f prime of t, and then it should be f of naught. Sorry for that. I mean, it's a typographical error. Should be f prime of naught, because eventually the right hand side should be independent of t, being the function of s. So it's f prime of naught. Typographical error. Anyway, we will utilize this in the upcoming slides. Take an example. Use the above theorem to find the following Laplace transforms. It's not a new thing if you look into that. Laplace of 1, we already know that it's 1 upon s. Laplace of t is 1 upon s squared. Laplace of e raised to power a t is 1 upon s minus a. But by utilizing this theorem, Laplace transform of derivatives, we can quantify. We can double check the Laplace transform of a constant polynomial of degree 1, exponential function, and many more. So take an example with part number 1, when f of t is equal to 1. No, remember the value of the function of t is 1. For what value of t? For any value of t. So if you take t equal to 0, the value of the function will be unchanged because it's constant value. So if f of t is 1, surely f of 0 will also be 1, because it is going to be a constant value. Whatever the value of t is taken, function is a constant value, so it does have a constant value, so it will turn out to be 1. And if you take derivative to a constant function, so it will turn out to be 0. So these are the components to be utilized. If you look into the formula for the first derivative, so here you go. Laplace of f prime of t should be equal to s times Laplace of f of t minus f of naught. So these are the things we are interested to keep. So we need to keep an eye on f of t. Yes, it's there 1. We must have f of naught. Yes, it's there 1. And we also have computed f prime 0. So these are the things we need to provide. F prime 0, f of t 1, f of 0 is 1. Since we are interested to find Laplace of 1, so rearrange the terms and eventually you will see that Laplace of 1 is going to be 1 upon s. Similarly, you can look into the other parts of this example. We move on to look into Laplace transforms of integrals. Provided that we know the Laplace transform of the original function f of t as a bar of s, then the Laplace of this integral will turn out to be Laplace of f of t as a bar of s divided by s. Carefully, if you look into the integral, we know that Laplace is taken against a function of t. But you see that integrand is a function of variable x. But keep an eye on the integral. X is a dummy variable, and eventually if you complete the integration inside those curly parentheses, it will turn out to be a function of t. And this is all. The Laplace of function of t, in that case it's an integral, will turn out to be a bar of s upon s. Once again, sorry for that. All right, so we have to go back again. Yep. So we are talking about Laplace transforms of integrals. Keep an eye. We know the Laplace transform of the original function f of t is there. Only then we can compute this one as a bar of s upon s. So we are interested to go into the proof of this one. So what we do, whatever inside the curly parentheses are there, it's a combination of multiple factors. Integral sign is there, limits of integration are there, integrand, variable of integration, multiple things are there. So we take this whole expression inside the curly parentheses as u, for example. And since we know that the outcome from the right hand side will turn out to be function of t, so it should be a function of t. So this is how we have u of t. If you integrate the right hand side, whatever the outcome is there because of the upper limit is a variable. So eventually the outcome is going to be function of t. So this is all. Our assumption is that this whole thing is going to be function of t. Then by the property of definite integrals, what the property is, if f of u is an integral over the interval from a to u, a is going to be fixed value, u is a variable, then the derivative to the left hand side with respect to u will turn out to be function of u. The fundamental property of definite integral. I mean, to the right hand side, if you take the derivative with respect to u, integral and derivative, they will cancel out, and we left with f of u to the right hand side. I mean, this is the fundamental property of definite integrals. So we are interested to find Laplace of this whole thing, and this whole thing is assumed as u of t. But since we are going to utilize the first derivative over there, so by keeping an eye on this fundamental property of definite integrals, derivative to u with respect to t from the right hand side, it will turn out to be function of t, just like this thing. From the right hand side, if you differentiate both sides with respect to u, from the right hand side, you will get the original function back. What the original function is, it will be function of u, small f of u. So if you differentiate both sides with respect to t, so the right hand side, you will get the original function back, and the variable will be t. So here you go, f of t, if you differentiate both sides with respect to t. We know u of t is equal to this one. If you take t is equal to 0, for example, to the right hand side, it's an integral over the interval from 0 to 0, nothing is there. So this is how we will be having 0. Now if you go back and look into the formula for the derivative, once we take Laplace transform on both sides of this equation, taking Laplace transform on both sides of this equation, to the left hand side we have derivative. So and we know the formula, s times Laplace of u of t minus u of naught. To the right hand side, it's Laplace of f of t. Plug in all these values, u of t. So we know that it is going to be that integral. What is u of naught? It's there, Laplace of f of t. And we know Laplace of f of t is f bar of s. So plug in all these components, u of naught 0, Laplace of f of t as f bar, and this s could be taken to the right hand side. So it will turn out to be 1 upon s. What is u of t? It was assumed as this whole combination. integral over the interval from 0 to t. So this is how we prove it, that the Laplace of that particular integral will turn out to be f bar of s, which is Laplace of f of t upon s. So as far as the implementation is concerned, nothing complicated is there. We already have an idea behind the scene about the Laplace transformation of multiple things: constant value, polynomial of certain degree, exponential, trigonometric functions. So it should be divided by s when we look into the Laplace transformation of an integral. For example, we are interested to find Laplace transforms of the following integrals. So prerequisite is there. We should know the Laplace transform of the integrand. So here, f of t is basically cosine of 3t. And from the previous table, we know the Laplace transform of cosine of 3t is going to be function of s. How do we write it down? S upon s square plus a square. A is multiple of t, cosine of that angle. AT, for example, we know the generalized formula. A is going to be 3 here. So this is all s upon s square plus 3 square means 9. And if you are interested to find the Laplace of this thing, and we know the formula, it will turn out to be Laplace of this expression, the integrand, divided by s. Since Laplace of this thing is going to be s upon s square plus 9, so this whole thing should be divided by s. So eventually s will cancel out by utilizing the property, take it in the numerator with same base. 1 minus 1, 0, so s raised to power 0 will turn out to be 1. So eventually we will be having the Laplace of this integral, 1 upon s square plus 9. Now the final component, before we move on to initial value problems, inverse Laplace transform. Pretty simple idea is there. If you are having an idea about the foundation for the Laplace transform of different expressions, inverse is going to be the other way around. For example, if the Laplace transform of a function of t, f of t, is f bar of s, then the inverse to f bar of s will turn out to be function of t. So remember, Laplace is from t to s, and the inverse will turn out to be from s to t. We go back to the original. We go back to the foundation. Foundation is f of t. We take the Laplace to have an expression in terms of s, and then the inverse will take back to f of t. So in other words, taking inverse on both sides. We will be having inverse to f bar of s as f of t. Find the inverse Laplace transforms of the following functions. If you take an example like that one, f bar of s is 1 upon s. No, you should be aware of the previous table for all sort of Laplace. Laplace of t, we know that it is 1 upon s square. So inverse will only come in that particular fashion if we know the Laplace transform. So we know Laplace of t is 1 upon s square. So then the inverse to this one, 1 upon s square, is equal to t. Pretty simple. Only if you know the Laplace transform to the expression given in terms of s. We have been given f of s, so you need to find the corresponding f of t. So by taking the inverse on both sides of this expression, because this should be compatible with the given expression. So we know from the table, Laplace of t is 1 upon s square, that one. So the inverse to this one will be equal to t. So here you go with the table, pretty much the same thing as we have done in the previous lecture. The Laplace transformation of a constant is going to be 1 upon s, of a polynomial with degree 1 upon s squared. Many ways you can look into the table, because we know the Laplace of t squared is 2 upon s cube. That too could be taken to the right hand side in that particular column. Some authors, they prefer to take in that particular column, and if you are not keen to do that, you can also keep it over there. So since the Laplace of t square was equal to 2 upon s cube in the previous table, so then the inverse to this one will turn out to be t square upon 2. So these are the same formula. So you reverse the direction in the loose term to get back to the original function of t. Pretty much in the same way, we can also look into the inverse version of the previous Laplace transform theorems. So we have gone through quite a few theorems in the previous lectures. So just like if Laplace of 1 is 1 upon s, so then the inverse to 1 upon s will turn out to be 1. Pretty much on the same line, you can also look into the inverse version of the previous Laplace transform theorem. So we will try to highlight that wherever it is applicable or wherever it is needed in the upcoming slides. Convolution. Sometime, of course, we do have an expression as a combination, as a product of more than one. So if we have f of t and g of t being two piecewise continuous functions, then the convolution of them, the combination of them, is going to be denoted by f asterisk g. This is special notation is there, asterisk for convolution, and defined as f asterisk g, since they are function of t, so will turn out to be an integral over the interval from 0 to t. F of t will turn out to be f of u, whereas g of t will turn out to be g of t minus u du. I mean, this is the definition. T for f is going to be replaced by u, whereas t for g is going to be replaced by t minus u. And eventually we have to integrate that one. Since u is a dummy variable to the right hand side, so eventually you can observe that it will turn out to be a function of t, the right hand side. Find the following convolution: 1 times 1, 1 times cosine of t, t times e raised to power t. So the formula is there. F of t, for example, is 1 is there. So t is going to be replaced by u. So u will be having f of u. If it is a constant, going to be unchanged, of course. But if it is a variable, should be changed. Like in this example, f of t is t. So inside the integral, f of u would be u. And g of t is equal to e raised to power t, means g of t minus u would be e raised to power t minus u. Very simple. T for f is going to be replaced by u, and t for g is going to be replaced by t minus u. So t is there, is going to be replaced by u, and that t is going to be replaced by t minus u. So this is how we look into the convolution. So here you go. By taking the third part of this example, t by formula is going to be replaced by u, and that t is going to be replaced by t minus u. Since we have to integrate with respect to u, so e raised to power t could be taken outside this integral. For the rest of the part inside the integral, integrate it by parts, and eventually you will be having that expression. Apply the upper and lower limit, and eventually it will turn out to be e raised to power t minus 1. Keep an eye on the formula. The rest of the part is going to be simple integral. you need to break the integral to get the expression as a function of t. Convolution does have property. If you remember from the assumed knowledge, you know the group has certain properties behind the scene. The associative law is there, the commutative law is there, distributive law is there, identity law is there, inverse law, pretty much on the same line. We do have properties for convolution. The convolution obeys the following properties. F aesthetic G is equal to G aesthetic F, and this is known as commutative property. I mean, if you replace them one by another one, swap them F by G and G by F, you will get the same answer. Like in this case, T aesthetic e raised to power T has this expression. If you swap them, e raised to power T aesthetic T will turn out to be the same answer. Associative property is there in case you have F, G, and H. Distributive property is there. F static G1 plus G2 will turn out to be F static G1 plus F static G2. And of course, if it is 0 multiple of F or 0 multiple of G, it will be 0 over there. I mean, if one of the, you need to check that. If, for example, one of them is 0, so eventually you will be having same answer, whatever the outcome is there. But if you multiply by 1, for example, you can never get G. 1 aesthetic G is not going to be G. As an example, for example, if you take G is equal to T, then apply the convolution 1 aesthetic G. So this is our f of T, and G of T is there. So f of T is going to be replaced by f of U. Since it's constant, going to be unchanged, but G of T is going to be G of T minus U over the interval from 0 to T. Integrate first with respect to U and then apply the limit. Eventually you see that it will turn out to be T square upon 2, whereas G of T was equal to T. So T square upon 2 is not equal to 2, is not equal to T for you in this case. So this is how we say that 1 aesthetic G. Generally we believe that when you multiply a function by 1, you get the original function. But in this case, convolution 1 aesthetic G is not going to be the same function. And of course, sometimes we are having an expression in the multiple form. So there is a theorem known as convolution theorem, the inverse to that combination, the product. If we know the Laplace of f bar of s as f of t, we know the Laplace inverse of g of s as g of t, then the Laplace inverse of this product will turn out to be convolution. And from convolution, we know the formula. How do we simplify this one? We know the formula. This is the formula, and eventually this is how you will get the function of t. Take an example. Using convolution theorem, we have to find the inverse of this combination. You see that it's not a simple expression. It's not one function of s, because you have to break them. So 1 upon sk times s minus a. So many ways you can handle this one. Keep an eye on the inverse to 1 upon sk, because you have to have the inverse of f. You have to have the inverse of g. So if you do separate them, for example, because the formula says that there should be product f bar of s times g bar of s. So you can separate them 1 upon sk as a bar and 1 upon s minus a as g bar. So to f bar, there should be Laplace. To g bar, there should also be Laplace. So what is Laplace of inverse of 1 upon sk? We know that t is there. And then 1 upon s minus a e raised to power at from the table. we have inverse to the first product, our first factor over there. We have the inverse to the second factor over there. So the first one is t. For the second one, it's e raised to power at. So it will turn out to be, if you keep an eye on the formula, Laplace inverse of f bar of s times g bar of s will turn out to be f of t aesthetic g of t. So f of t in this case is t, and g of t is e raised to power at. So t aesthetic e raised to power at. From inverse to convolution, and then we know the formula. T is going to be replaced by u e raised to power at. So t for g is going to be replaced by t minus u. Simplify that, and eventually you will be having this answer. Sometimes there could be, the typographical error, or you can double check that the answer is going to be that one. There might be a typographical error, but eventually, if you do simplify this one, the answer is going to be function of t like that. All right, finally, we look into the application. Application of Laplace transform to initial value problem in the form of initial value problem. So we know that what the initial value problem is, a problem together with initial conditions. There might be a single condition. If there is one condition, regardless the value of t means the independent variable, it is going to be initial condition because there is only one condition is there. If you have more than one conditions, then you need to look into the aspect whether the conditions are going to be initial or boundary. If all the conditions are subject to only one value of the independent variable, then the conditions are going to be initial conditions, and the problem together with the initial conditions is known as initial value problem. And if the conditions are subject to more than one values of the independent variable, then the conditions are known as boundary conditions. And the problem together with boundary conditions is going to be boundary value problem. We will look into the initial value problem. Means problem is there, the mathematical formulation is there in the form of differential equation together with initial conditions. What is the procedure behind this? If we have an initial value problem, so there are three essential components. Number one, take the Laplace transform of the given differential equation. Then we need to apply the initial conditions to obtain an algebraic equation, and then solve this equation for the Laplace transform of the required solution. Take the Laplace transform, this is the half part, get the algebraic equation, simplify that algebraic equation, get the solution of the algebraic equation, and then eventually take the inverse Laplace transform to get the solution of the given initial value problem. So we have to use Laplace. We also have to use inverse of Laplace. And the middle part is going to be the solution to corresponding algebraic equation. So these are three essential components that we have to keep an eye on. When we look into the solution of initial value problems using Laplace transform, we try to take few simple examples. Like we have a second order differential equation, y double prime plus y is equal to 0. It's homogeneous because of the right hand side is 0. Keep an eye, y is going to be function of t. By default, y is going to be function of t. So y double prime is, it's a second rate of change of y with respect to t. Together with initial conditions are there. Y of 0 equal to 1 means when t is equal to 0, the value of y is 1, and the value of y prime is minus 1 when t equal to 0. Since we have multiple conditions, more than one conditions, but they are subject to only one value of the independent variable t, it's 0. So these conditions are known as initial conditions. Together with the problem, it is known as initial value problem. So this is how we have to simplify that by using Laplace transform. So very first step, taking Laplace transform on both sides of this equation. It's a second derivative, and we know the formula. Keep an eye on the formula for the second derivative. We have gone through with that. So s square y bar of s minus s times y of naught minus y prime of naught. So Laplace to y of t is going to be y bar of s. So it's a different notation. In the previous slides, we have utilized f of t. No, instead of f of t, we have y of t. So Laplace to y of t will be y bar of s, and derivative is second over there. So this is going to be the expression. We have everything now. Y of 0 is there, plug in. Y prime of 0 is there. So plug in all these values and simplify that. So once we simplify that, we will be having y bar of s. Now you see that it's independent of derivative. So this is all. We call it algebraic equation. The first one is differential. Now it's an algebraic equation. By using the initial conditions, the given conditions, we are having algebraic equation. Simplify that. So how do we simplify that? We are going to separate them by using partial fraction. Now you see that it's one component. We can easily find the inverse to that one. Same is the case, we can find the inverse to that. So keep an eye on the formula. So sk s upon s square plus 1 square. So a upon s square plus a square, a is going to be 1 in both cases. So keep an eye on the formulas. So if you take the inverse on both sides, so inverse to y bar of s will be y of t, and then the inverse to the first is going to be cosine, the inverse to the second is going to be sine. A is going to be 1 in both cases. S upon s square plus 1 square. So 1 is basically a in the table. So a upon s square plus a square. So this is all. We will be having the corresponding function. It's non-homogeneous because of the right-hand side is going to be non-zero. It's a function of t. So same step. Taking Laplace, second derivative formula is there. Laplace to y bar of s, and Laplace of e raised to power t, 1 upon s minus a. And the second step, apply the initial condition and simplify it. So here you go. Simple procedure is there. Algebraic equation is there. Get the solution of this one. Means you need to find y bar of s. So eventually, if you separate them by using the partial fraction, and eventually we will be having 3 factors over there. 3 simple factors over there. And the very last step, we need to apply the inverse of Laplace. So applying that, so 1 upon s minus 1 e raised to power 1t. 1 upon s minus 3 e raised to power 3t. 2 can be taken sideways. 1 upon s plus 3 means minus outside, inside the bracket, minus 3, for example. So this is all e raised to power minus 3. So inverse to the first factor, inverse to the second factor, inverse to the last factor. So this is all. We will be having the outcome. We can also look into the application in terms of system of equations. So we are having 2 equations now. System. Whenever you combine more than 1 equations as 1 unit, it is known as system. So in the system, we have 2 parameters, y1 and y2 over there. So pretty much the same procedure is there, taking the Laplace transform on both sides of the first equation as well as the second equation. So Laplace to y1 prime by using the formula. Laplace to y1 bar of s, Laplace to y2 bar of s. To take the Laplace to the second equation, to the left hand side, first derivative formula is there. y2 bar, y1 bar. So plug in all the values. We know y of 0. We know y2 of 0. So plug in those values. So once we plug in, simplify them, it's a system of algebraic equations. looks to me a bit complicated, but they're very simple expressions. It is just like x and y. I mean, just think about that. y1 bar of s is x and y2 bar of s is y. Then it is s minus 2 times x plus 3 times y equal to 8. And from the second equation, 2 times x plus s minus 1 times y equal to 3. And then you have to simplify that. Plenty of options are there. For the solution of system of linear equations, the starting one is known as Cramer's rule. And it is going to be wonderful if there are not too many equations in the system, like 2 by 2. Matrix is there with 2 equations involving 2 unknown. One of the best option is a very fundamental rule known as Cramer's rule. So if you apply Cramer's rule, you will get the values for y1 and y2. So this is the solution of the system is there. We have to find those 2 unknown, y1 and y2. So they are going to be function of s. y1 simplified form, y2 simplified form is there. And finally, by taking the inverse to y1, bar of s will turn out to be y1 of t. Inverse to y2, bar of s will turn out to be y2 to the right hand side. Simple expressions are there again in terms of exponential function, exponential function, exponential. So this is how the solution is there in terms of y1 of t, y2 of t. One more example, pretty relevant to electrical engineering. RLC circuit is there. We have gone through with that. RC, LC, RLC circuits, different types of the circuits are there. So an RLC circuit has a resistance. Resistance of 10 ohm, capacitance of that much, inductance of 0.5 Henry being the units, and an applied voltage, constant value is there, 12 volts. And on top of that, no initial current and no initial charge on the capacitor is there. I mean, these are the initial conditions. And you must be well aware about the current and charge. The time rate of change of charge is going to be current. So using the method of Laplace transforms, we need to find an expression for the current flowing through the circuit at any time t. It means as a function of t, we need to find current. So of course, we have to go into the modeling, and we have gone through that. What will be the mathematical model of an RLC circuit? We know that. It will turn out to be second order differential equation. If you label charge as Q in RLC circuit, then the differential equation will turn out to be of this form. So the second order differential equation, quite a few unknown parameters are there, RLC, but we know R as 10, C 10 raised to power minus 2, L 0.5, electricity is going to be fixed, 12. So plug in those values. So this is going to be second order differential equation in the dependent variable Q with the independent variable T. So now you take start talking about those 3 steps. The first step is about the Laplace transform of Q, Q prime, and Q double prime. We know those formulas for double derivative, for first derivative, for the function. So for the function Q of t, it will turn out to be Q bar of s. With first derivative, second derivative formulas are there. To the right hand side, since it's a constant value, so it will turn out to be 24 upon s. So this is the first step, taking Laplace transform. The second step is that we need to apply initial conditions. What the conditions are? there is no initial current, there is no initial charge. So plug in those values. So Q of 0 is 0, Q prime of 0 is also 0, the current. So plug in those initial values. Now, once we replace those values, the simplified form of the equation would be like that. Simplify that. So if you simplify that, it means that Q of S will be equal to that. A bit complicated expression is there in the denominator. So you need to play around, try to make it as simple as possible so that you can directly apply the inverse. So one way to simplify that as one of the appropriate form of the outcome is going to be that one. There could be more than one. Anyway, so this is going to be one of the appropriate outcome because eventually we have to take the inverse. So this should be compatible. Compatibility with the formula in the table, with those expressions that you make out of that expression. Finally, taking the inverse Laplace transform, we have now 1 upon s, inverse to that is 1. Constant value is taken outside. No, have a look at this one. S plus 10, S plus 10. So if you assume that it is going to be one fixed parameter, like W is there. So W upon W square plus 10 square, pretty much the same expression as we have in the table. So it will turn out to be cosine of 80 times e raised to power minus 80. A is going to be 10 here in this case. Same is the case with this one. So A is going to be S minus A square plus 10 square to that. So simplify that because of the adjustment over there, it will turn out to be 3 upon 25 because 6 upon 50 means 3 upon 25. And eventually this is all. The outcome is there. You need to play around with simple algebraic expressions, and this is all. Eventually you will find the outcome as a function of t. All right, so that's it. We wind up this particular topic up to that particular point, because this is all. The ultimate goal is there. With the Laplace transformation, we have to solve initial value problems. Got some time? If you have any query, please. Ahmed Asim is there. What is your query, please? I don't understand. Nibaz B, name Digo. What is this? So, inshallah, next time we will talk about partial differential equations. the extended version. We have gone through with boundary differential equations, and then the implementation is there in the form of Laplace transform. Mids कब होंगे? Still we are looking for the policy designed by the department or the university. So as soon I am informed, I will intimate you immediately. There might be only one examination at the end of the day. There might be. I mean, this is one of the perception. Anyway, we will look into that as soon as I'm informed about the departmental or university policy. So kindly share all the recorded lectures. So there are quite a few lectures. I think 5 or 6 lectures been uploaded. Go and look into them. Yeah, five to 6 are there. Some of the lectures, I'm trying to do that. They have some technical issues. I mean, they have to be edited before they've been posted. How many slides are left? No, all the slides are provided to you. So we have covered up to Laplace transformation. In the next lecture, we will talk about partial differential equation, inshallah. And then the last topic is the Fourier transformation. Plenty of things are there, of course. I mean, but we will try to cover as much as we can. So we normally try to talk about more essential components to be discussed. Okay, try to go through with the theory. And few related examples we normally try. And further, you can go into the reference books. No attendance. I have created the poll. I believe that I have created the poll. Go and mark your attendance over there. I believe that poll is there. Yes, 111. 111 students have responded to that poll. So 138, go and mark your attendance over there. Our related exercises as much as you can. Plenty of reference books are there. But I think, I mean, if you go with the topic, the theory is there and related examples are also there. So if you are interested for more practice, you can also look into the reference book. Because sometime what happened, not all the topics are covered or available in one reference book. So this is all. You have to try with the alternative option. Our reference book is Advanced Engineering Mathematics, reference book number 1. So they've been listed out of preference. Topic is there. And you can look into the examples for the example. But I believe that if you go through with the theory, it's more vital than anything else. Yes, it's there. It's there. You need to go and search online. Every edition does have a solution manual to advanced engineering mathematics. There might be more than one version. Remember, one is instructor manual and the other one is student's manual. But anyway, both are available. You need to search online. It's available. And for example, we normally talk about 10th edition. It's not like the textbook, remember. Not quite the textbook is there. If the solution manual to 10th edition is not available, you can also look into the 9th edition with solution manual. Whatever is applicable, whatever is available to you, you can practice from that. The main thing is to talk about theoretical aspect. Main thing is to talk about technical aspects. And that's what we try to do by going through with the slides with few examples. Yes, here you go. Yeah, 173. Follow that. All right, so if there is no further query, then thank you very much. See you inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.